This is static electricity part 2 of the lesson. So we'll start with coulombs, or letter C we give to coulombs, and coulombs are the unit of charge. We've mentioned this previously, but we'll talk about it a bit more. So we've seen that there are positive and negative charges, and 1 coulomb is equivalent or the same as the charge of 6.25 by 10 to the power of 8 electrons. Now, what's that? It's a really large number. Okay, so let's see. 6, and I'm going to move the decimal point 8 times, so that I multiply by 10 8 times. So this is 1, 2, 3, 4, 5, 6, 7, 8. So that's 625 million electrons have the charge that's the same as 1 coulomb. So that's a lot. But you may ask the question, or you could say that 1 electron has a charge of minus, because it's negative, 1.6 by 10 to the minus 19 coulombs. Now that's a really tiny number. Let's explore that. We have to move the decimal place 19 times, or divide by 10 19 times. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is going on. 11, 12, 13, 14, 15, 16, 17, 18, 19. That's my decimal point. So that many coulombs of charge is on 1 little electron. Okay, so you may ask the question, and I certainly did, how on earth was that measured? Okay, how do we know 1 coulomb is that many electrons, or that the charge on 1 teeny tiny electron is that very, very, very small number? Okay, and this is what? Okay, and it was an experiment called the Millikan oil drop experiment. And the oil drop experiment was performed by a guy called Robert A. Millikan and another guy called Harvey Fletcher in 1909. So they had the wherewithal to do this, to measure this in 1909, to measure the charge of the electron. So I'll talk you through it, and then we'll have a picture, and I have a link to a video on this. You don't have to know this for your course, but it's informative, because you'll be wondering, well, how do they know these numbers and how they went about it. It's also a lesson in how the experiments, while you cannot see the electron directly because it's so tiny, how we use in science the evidence produced by an experiment to come to a conclusion. Okay, so in 1909, these guys, they observed tiny charged droplets of oil, so they're tiny drops of oil, between 2 horizontal metal electrodes. So they had these circular metal discs, and they were connected up to a voltage, which makes them electrodes. Okay, they can conduct electricity. First, with 0 applied electric field, so with the power off, the terminal velocity of a droplet was measured. So they looked at a droplet falling under gravity, okay, under regular gravity, and they measured its velocity. How fast is it going? All right, so at terminal velocity is when gravity and the air resistance balance, and it travels at constant velocity. Okay, they also measured the radius and the mass of the droplets. And then what they did was they turned on the power, and they increased the voltage and decreased it, and they switched it around. They switched plus with minus. And we have learned that negative charges are attracted to positive because they are opposites, and negative charges are repelled from other negative charges because they're the same. So they looked at the motion and the speed of the droplets that were falling, okay, and compared it to the the speeds that they measured without any power switched on, so without any voltage, and they were able to make some calculations. So when they were using a known electric field, okay, we'll talk about the definition of that shortly, Millikan and Fletcher could determine the charge on the oil drop. So they could say what was the negative charge on the oil drop, and by doing that for hundreds and thousands of oil drops, okay, they saw that the answers for the charges were always small integer multiples of a certain base value. So the answer always came back 2 times a base value, or 4 times a base value, or 1 times a base value. And they concluded that whatever this base value was, you couldn't get a part of one. It was always one of them, or 2 of them, or 3 of them, or 4 of them. That this base value was the charge of a single electron. Okay, so you couldn't get in between values. So here's a diagram of the experiment. Like I said, you don't have to know this, but it's quite interesting. So we have a cylindrical type container. This is a cross section of it. Okay, and little oil droplets are pumped in from an atomizer. So you recognize it's like a perfume spray bottle. Okay, so the oil is inside in the container. By pumping this here, tiny droplets of oil are pumped into the chamber, and then those droplets fall down through the central hole in the disc at the top. Okay, and they can be observed here by a microscope. Okay, and they're very, very light, so they fall quite slowly, and their velocities can be measured, and that's what the experimenters did. Okay, and however, then what they did was they turned on the battery. Okay, so they watched them falling under gravity, they measured their velocity, they turned on the battery, and this plate was made positive at the top. Positive, I should write, positive, plus. Okay, so a little oil drop that had fallen and had its velocity measured here, if for example that had 3 electrons on it after being charged, it was observed then to slow down. Okay, was one of the observations. This bottom plate here was negative, and it slowed down because it was repelled from the bottom plate, because negative repels negative, and it was attracted to the top plate because negatives are attracted to the positives. And by measuring how much it slowed down, or indeed sometimes if they were very light and had only 1 or 2 electrons, they actually started rising up again. Okay, so by measuring the change in the speed when the power was turned on, they were able to calculate what was the charge on the oil drop, and they found that all of the charges were multiples of a certain set value, and they concluded that this certain set value was the charge on an electron. Okay, like I said, you don't have to know that, but it's quite interesting. And at the end, I'm going to provide you with this YouTube link to a short video on the Millikan oil experiment. Okay, now we're going to talk about electrostatic force. So we did force way back in mechanics, and we learned that it causes acceleration. So things don't move just because. They have to feel a force before they change their motion. Okay, so now we're going to look at the way that electrostatic charges, okay, can cause movement or a change in movement or acceleration. So charges exert forces on each other. We've already mentioned that. So we've said that opposite charges attract. So you saw in the oil drop experiment that changing the charges on the plate can cause the little oil drop to be attracted back upwards to the positive plate, and like charges repel. Okay, so there is a force there attraction is a pulling force, repulsion or repelling is a pushing force, and they are causing, or they can cause, acceleration. And the size of the force, so how strong is the attraction or repulsion, depends on a few things. It depends on the magnitude or the size of each charge. Okay, so if you have lots of coulombs, then you're going to have big forces, okay, and they're measured in coulombs. Also, the distance between the charges, d, measured in meters. So if charges are close together, they can feel the force much more easily than if they're far apart. And a third thing that it depends on is the medium or the material between the charges. So are they in a vacuum? Are they in air? Are they in water? Or perhaps they're on either side of a piece of metal or on either side of a piece of plastic. Okay, so all of those things, that's called the permittivity. This funny letter E, right? It's called epsilon is the name of the letter, and it's the permittivity of a given material. And what permittivity it means, it's the ability of material to resist an electric field being formed in it. Okay, we'll talk about electric fields in a little while. You don't have to understand too much about it, except that depending what's placed between the charges, the force can be fully felt or can be dampened or reduced somewhat if you place different materials in between. Okay. So, and what we've just discussed there is called Coulomb's law. And you'll find Coulomb's law, not this version, but the following version, in your formula and tables book. Okay, so what we've written in English before is now written in symbols here. It says that the force is proportional to, or depends on, the charges, so the size or the magnitude of the charges. So if you have two charges, Q1 is the first one and Q2 is the second one, and you have to multiply them. Okay, so if you double one, you'll double the force. If you double the two of them, it'll be 2 times 2, 4 times bigger. Okay, so the bigger the charges, the bigger the force. And underneath we have the distance between the two charges. Okay, and you can see, because we're dividing by distance, if the distance gets much bigger, well then the force gets much smaller. They're inversely proportional. It gets weaker. If they're further apart, they can't feel the force of one another so well. Okay, sorry, I've written over that. The electrostatic force between 2 point charges. Point charges just means 2 points in space. You have the charge there and there. Okay, is proportional to the product of their charges and inversely proportional to the square of the distance between them. Now we had something very, very similar, but on a completely different topic when we did gravitational force. Okay, in that one the force was proportional to the masses of the objects, so the moon and the earth, and inversely proportional to the distance between them. Now when you're asked to state Coulomb's law, you have a choice. You can write the formula, say what the letters stand for, or you can write the English, which is a little bit harder to remember. Okay, and in your formula books you'll find this version of Coulomb's law, and here you see that the force is equal to, so this one we can use for calculations, and here we have an extra part at the start, 1 over 4 pi epsilon, and that was, we discussed that on the previous slide, that's your permittivity. Okay, so it depends on what material everything is sitting in as well. Okay, there's your Q1 multiplied by Q2 divided by d squared. And this is an example of an inverse square law, okay, because we have 1 over d squared, and if we increase the distance, the force dramatically decreases because it's d squared, d times d. So if you double d to 2d, you're now dividing by force is proportional to 1 over 4 d squared, because you'll have 2 times 2. So it that's where the square bit comes in. Okay. So just to show you that, in the formula and tables booklet, on the contents pages, you would look for the electricity page, which is page 61. You look for Coulomb's law, and here you will see the equation we're just talking about. Okay, they use small letter q here. And we're going to use that here in the following example. If 2-point charges of -3 microcoulombs and +2 microcoulombs are placed 25 centimeters apart in air, what is the magnitude and direction of the force on the +2 microcoulomb charge? And we're given the permittivity of air there also. So lots to take in. When we talk about 2-point charges, we're talking about 2 points in space. So one was minus and one is plus, and we measure them from center to center, and that will be the distance between them, and we're looking to calculate what force do they feel. So for that we'll need our Coulomb's law. Before we go there, let's talk about microcoulombs. The prefix micro uses this mu letter, means multiply by 10 to the minus 6, okay, or divide by 10 6 times. So it's a very, very small charge, and here we have the same for the 2, okay. So micro equals 10 to the power of -6. And they're placed 25 centimeters apart in air. Well, clearly that's the distance, but centimeters is not the standard unit for distance. What is it? It's meters. So to change centimeters, centi means 100, so it'll be 25 over 100, which is 0.25 meters. So we'll use that for distance. And the permittivity of air is given here, 8.9 by 10 to the power of -12. So it's a very small number again, 8.9, and it would be divided by 10 12 times. Okay, now our scientific calculators are able to deal with all those very small numbers very well. So first what you do is you recognize this is Coulomb's law because the word force is mentioned. Okay, so you would write down from the formula books your formula for Coulomb's law. And the second step then is to insert the correct figures in the correct place. Okay, so this is what we have here. So the first part of it is 1 over 4 times pi. Now your calculator will insert pi if you use it, or you can use 3.142, or you can go to as many decimal places as you like, times 8.9 times 10 to the power of -12. That's the first fraction, multiplied by, and then I'm using brackets just to separate those things so I can see clearly. The -3 microcoulombs comes first, multiplied by the 2 microcoulombs is second, and underneath I have 0.25 squared. Now on the next slide I'm going to show you how to enter that into your scientific calculator correctly. Okay, so showing you how to enter that on the scientific calculator. Firstly, it takes the form of 2 fractions, so we're going to use the fraction button here. So first fraction is 1 over
So use your down arrow to go underneath. 4 times. Now if you see here, this button at the bottom, you can see the yellow letter pi, so we use shift and pi. We'll type that in for us. Multiplied by 8.9 and to the power of minus 12. So this is where I can use this button at the bottom. Also by 10 to the power of x. So just press it and you don't have to type in the number 10. We just enter now the power that we want to use. So I'm going to use this negative button here, negative 12. Okay, and it looks a bit odd, but that's correct. And that's the first part of the fraction complete. Now, using the right arrow, we go across and we can do multiply by. Now let's fill in the second fraction. So I'm going to type it exactly as we had on the previous slide. I'm going to use brackets to show multiplication. I like to use this negative button instead of subtract when we're just showing a negative number, because in certain circumstances they can get mixed up. Okay, so minus 3. Again, we're using this power button at the back, or at the bottom, it's called the exponential button, by 10 to the power of negative 6. Close the bracket and then open the next bracket, and that's 2 multiplied by, sorry, I don't need to do that here, delete, 2 and the exponential button, negative 6. It's my microcoulombs. And then underneath there, so use the down arrow to go down, and I'm going to type in 0.25, and that needs to be squared, so use the square button. Okay, now if you want to review what you've typed in, you can use the left and right arrows to go backwards and forwards. Okay, but when you're happy with that, just press equals and you'll get your answer.
So you see there that the force was minus 0.8584 newtons, and just like every other force you have studied, the unit of force is newtons. Okay, so what about direction? So if you recall at the beginning, we had one positive and one negative charge, so they should be attracted to one another, and that's what the minus sign indicates. It's an attractive force. Okay, so they are opposite charges, so the force will be attractive, and the question asks specifically about the force on the +2 microcoulomb charge. So the force on the 2 microcoulomb charge will be towards the -3 microcoulomb charge, and it will be of the size above, 0.8584 newtons. So next is electric fields. Now we've kind of mentioned them on our way here, and the definition of an electric field is: an electric field is a region of space in which a charge exerts a force. So it's the region of space around a charge where other charges can feel it, can feel a force from it. Okay, we can't see it, but we can detect it from the movement of other charges. And we can draw it using electric field lines. Okay, so just please note, in reality there's no such thing as these lines. We use them to depict or picture the electric field. Okay, electric field lines are used to show the direction, which is always positive to negative. Okay, and the strength, so which is shown by the concentration or number of lines of a force felt by a positive charge in the field. So to draw an electric field, we use these imaginary lines, and we use them to show what would happen if you dropped a positive charge into the picture. And it can be seen that the field is strongest closer to the charge, which it should be. And attractive and repulsive forces are seen in the diagrams on the next slide. So we'll look at those. So here we have a diagram that shows the electric field created when you have a positive charge, one positive and one negative charge. Okay, so we said we have to imagine what would happen if we drop a positive charge into this picture. So let's drop a positive charge right into the middle. Well, it would be repelled away from its like charge, so it will go away from, be pushed away from the positive, and it will be attracted towards the negative. So there we get the direction of the lines. Okay, if you drop it one out here, positive, well, it's going to be attracted towards the negative. That's where we get that line. And then you have some variation on that in between. If you dropped it out here, it does feel the positive somewhat and goes towards the negative. So away from positive and towards negative. Okay, and you can see in general that these two charges are joined by lots of lines. And if they're allowed to move freely, well, the positive would probably move towards the negative and vice versa. Okay, so this shows attraction, okay, between opposite charges. Now, what does it look like if you have two similar or two like charges? Okay, here we have two positive charges. And let's do as we did before. Let's imagine if we drop a positive charge in there, it will be pushed away from that positive. And likewise over here, if you dropped in a positive, it goes away. So all the lines are going away from the positive charges. And look at the pattern of the lines. They don't overlap. Okay, they don't cross over. And if you can imagine them as wires, metal wires, if you were to try and push them together, you'd feel a resistance that they would push back, and that shows a picture of repulsion, or two like charges repelling each other. Okay, they push apart. Now we have applications of static electricity. So we talked about how to create charge and the way like charges repel and unlike charges attract. We were able to create charge using friction. So what are the applications of this? What are the practical uses of it? And one would be your office photocopier. Okay, so when you place a page on the photocopier and you know that the light passes over it, what it does, it creates a pattern of static charges on a plate. Okay, so that's what's happening in stage 2. All right, and stage 3 here then has the ink, and the little ink particles have negative charges in this case. Okay, and they're attracted towards the positive pattern that has been created, and so they get attracted to it and they stick to it. Okay, and then we have negative charges in the correct pattern or picture, and then the page is passed over, which has positive charges, and the ink sticks to it. Okay, so negative being attracted to positive again. Okay, so that's a very useful application of static electricity, the photocopier. So here's the steps of what happens. Positive charge is put onto a plate by friction. The plate has earth connection, but the charge is not energetic enough to escape yet. Okay, don't mind that. Number 2, paper placed over the plate and the light is shone onto the paper. So the illumination allows the extra charges to escape to earth, and what remains is what was covered by your the pattern or the picture on your page. Negative toner particles are then sprayed and they adhere or stick to the charged parts on the plate. And finally, the paper is given a positive charge which attracts the toner particles. And then you have replicated or copied your original pattern. Okay, defibrillators. Okay, they're used in emergency medical services. Okay, if your heart needs resetting or restarting. So you've seen it on the medical programs on TV, I'm sure. So they shout clear and charge, and so the two plates become charged. Okay, a defibrillator is a machine that can be used by paramedics to restart your heart if it stops. Two paddles with insulated handles, that's very important, are charged from a high voltage supply, so really high charges here. They're put in good electrical contact with the patient's chest, and it's important that no one else gets a shock, which is why the paddles have insulating handles, and the operator tells anyone nearby to stand clear. And then a charge is passed through the patient to make the heart contract and to reset it, really. Okay, so that's defibrillators. Here's another application for electrostatic dust precipitators. Now, what are they? They're fitted to factory chimneys. Okay, so when smoke particles are leaving the chimneys, they are charged. You can see that as the smoke particles pass up here through this blue grid, they become charged. Okay, and the next step is for them to pass by these red plates which would be oppositely charged, and we know that opposites attract, so the particles then stick to it, and these are called collecting plates, and then these can be removed from the collecting plates into somewhere that collects them, okay, and then removed from the chimney. So it's like a filtering process. And yes, static electricity is used a lot in paint spraying or galvanizing. So when spraying cars and stuff like that, there can be a lot of waste from spray paint. Okay, a lot of it misses where it's supposed to go or gets the surrounding areas. Okay, so if the car is made to have a charge in positive or negative, if the paint particles are oppositely charged, then they are more likely to go and stick to it and not miss it completely, and also it gives a very even coat. Okay, so you can read that there yourselves. Okay, dangers of static electricity. We spoke about lightning, which is a big one before, okay, and why we have lightning rods on the top of very tall buildings. Okay, that's one. The other one is if charge is allowed to build up, okay, and there happens to be flammable gases in the area or a high concentration of oxygen, then a spark due to too much static electricity and something discharging can cause an explosion. So that would be a worry. In certain industries where there may be flammable gases around, the workers in such areas wear special clothes that don't create any friction, any static charges from friction and that. Okay, so again, you can read that yourselves, but I have some videos following, some links for videos that go through some of the applications as well. Okay, so these links will be posted on your team, your physics team, and you can have a look at those three also. So that's the end of the static electricity lesson, and I'm going to write a quiz for you to complete also based on that.